Hi everyone. So now we're going to go into the determinant and trace of a linear operator. So if you've seen determinants of matrices and traces of matrices, this is basically the same idea, but we're going to be applying them to the matrices of linear operators and kind of seeing some of the principles we're going to be using for later on. So some of this might be very easy for some people, but you can put this video on 2x speed and go from there if you'd like. Okay, so first we're going to define what a determinant is. So if we start off with some n by n matrix, so we have n by n, so yeah, some big n by n, so n. The determinant of the matrix is defined by this nasty fun little formula. So here we're going to take the sum. This is going to be all the permutations in the group of permutations. So this is just permutations. If you don't know what these are, come ask either David or myself, and we can kind of go over them with you. Then we take the sign of a permutation. And then we finally take the product of our matrix, where the indices of our matrix are precisely the ith and sigma ith entry. So here we have I is equal to 1 to n. And that gives us the determinant. Seems big and complicated, but for our purposes, there's two main determinants we really care about that we'll be using frequently. So the first one is the 2x2 case, and the second one is the 3x3 case. So in essence, for the 2x2 case, we have like a little x, right? AD times minus BC. The 3x3 case, there's many different ways to kind of see this. But in essence, what we kind of, what I'm used to doing is you put a little plus minus plus on top. That helps you realize what the things are. Then we do A and the determinant of A. So this is what this part is. And this is a plus in front because I have a plus on top of the A. Then if I look at B, for example, B here, B is negative because there's a negative on top. And then I look at the sub matrix without B. So here I have DG Fi. So that gives me part B. And then C I won't draw or else it might get a little too crowded. I'll just put a little C on this one. So here we have a plus C. And obviously we'll get the left two columns for that. And this is how the determinant is working. So in essence, if you take this and go higher, this is how, in essence, we're doing the determinant in higher dimensions. So, like, for example, if I have a 4x4, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. The idea here is basically first you do your plus minus on top, and then you do exactly that. So this is then going to be A determinant of the blue part. And then we'll do a different color, then minus B of the determinant of this pink part, etc. And then so plus C determinant, and then minus D determinant. And that's all this is. You just do this inductively all the way down until you have a formula. That's what this big formula on top is basically trying to do. That's what this is what that's doing. That's it. So some properties on determinants that most of you have hopefully already seen. And that is the following, that M is going to be invertible. We've already talked about this. If and only if the determinant is non-zero. We should already know that if I take the multiplication of two matrices, the determinant just multiplies as well. We've already seen that the determinant of the transpose is just equal to the determinant itself. And for any scalar, I can basically pull the scalar up, but I have to multiply it n times, right? Because it's going to kind of be everywhere. So I have to pull this n times out. Now, because of the determinant, the determinant of the identity is equal to 1. What we also end up having is the following. So we can kind of show from number 2 that if M is invertible, then the determinant of the inverse is equal to the inverse of the determinant. So it's pretty nice. So that's determinant. This is something we should have seen before. Next up is the trace. Again, this is something I'm assuming most of us have seen before. So here it's an n by n matrix again. And what's the trace? Well, it's just the sum. This one's a little easier. The sum of what? So we take our matrix and we look at the diagonals. So if I have M is equal to something, right? The trace is the diagonal. So we just sum the diagonal. That's it. So let's look at, similarly like we did for the determinant, let's look at some properties of the trace. And it turns out it satisfies the following properties for a trace. So we have that if I try to add two matrices together, well, the trace, we can just add the traces together. Now this logically kind of makes sense because I'm not really, when I add two matrices together, I'm just adding the middle entries, right? Nothing really affects anything else. If I have the trace of lambda of M, this is just, we can pull the lambda out. What happens when I multiply M and N? Well, in essence, because I'm looking at the diagonal, what I have is that the order doesn't matter. So I can just flip these and these are the same. So that doesn't necessarily mean that Mn is equal to Nm. So here I should put a little note. Does not imply Mn is equal to Nm. Which makes us sad, but this is, oh, you can't see. This makes us sad, but this is kind of life. Like, this is not generally true. But the traces are in fact the same. So it's nice. Now, if we look at the trace, these first two properties should kind of make you think of something we've been seeing quite a few times already. And that is precisely the idea of linearity, right? So these two properties are basically giving us linearity. In other words, the trace of lambda m plus mu of n is just lambda trace of m is equal to mu of trace of n. Right? Oh, not equal, sorry, plus. And again, you cannot see, yo. There we go. As an aside, we're also going to remark that any map that takes matrices to scalars satisfying these three conditions. So if it satisfies 1, 2, and 3, satisfies propositions 1.48, then this must be a scalar multiple of the trace map. So in other words, anything that satisfies these three properties gives us, in some sense, the trace map up to scalar multiple. Okay, so let us, how long has it been? Yeah, so let's give us two quick definitions, or a proposition and then a definition, and then, or two definitions, and we'll call it for this video. So the proposition that's up next is that if I take the determinant of, so I have some linear operator P, and I have two different bases, B and C, right? So I want to see the determinant of the linear operator P with relation to B. What is this equal to with relation to C? So if I look at it over a different basis, how does this kind of work? And it turns out they're actually, that looks like a sum. It turns out that they're actually just identical. The determinants are the same. And as you can probably guess, the traces are also going to be the same. I mean, you can have kind of guessed that if you had looked at the proof, but I'm assuming we haven't gone that far yet. So the proof of this is basically just a quick calculation on this. So this equality is exactly the proposition we saw a little while ago. Where was it? 1.43. Is a 1.43. This is properties of determinants, and this is basically 1.46, right? So since these are, and then finally here we move this one over, right? So the trace is going to be its inverse, and this was like a little remark we had. And since these are numbers, right, we can move them around. So these two cancel with one another. These two cancel. And that just gives us the determinant of PB. And the trace is done almost in a similar way, right? So here we're just using the fact that we can move these two around and we kind of get happy. So yeah, so that's a nice easy proposition. And then two definitions real quick. And that's the determinant of the linear operator is precisely what we're kind of going to be assuming it is. We'll say the determinant of P, this is just going to be the determinant of its matrix. So not too bad. Similarly, the trace of P is going to be the trace of its matrix. So a lot of this is kind of just here for notation. But the point is the reason why we can do this, right? The only reason we can do this is because the determinant stays the same, right? So because of this proposition 1.5, determinant doesn't change on our choice of basis, which means we can think of the linear operator itself as having this value. So the determinant of the linear operator is going to be the determinant of one of these matrices. I don't really care which one, just choose one of them. And hint, the kind of nice one to kind of choose is the canonical one. So choosing the canonical one, the standard orthonormal basis, is a nice choice to kind of get this nice and easy. Yeah, so this is basically, this remark is exactly kind of what I said. So it requires a choice of basis, but once we've actually chosen it, it doesn't really matter because the determinant value is going to stay the same. Okay, so I will end this video here. And in the next video, we're going to talk in German, and we'll talk about eigenvalues and eigenvectors of linear operators. Don't worry, we won't actually speak in German. I don't actually know German. But I will see you then. Peace.